the basics of simple harmonic motion with a fet applet based around a mass on the end of a spring. So we have a couple of sliders here, here and here. This one allows us to adjust the mass at the end of the spring. This one allows us to adjust the spring constant. A large spring constant allows us to have a thicker or stiffer spring. You see that? Smaller spring constant, the spring is more relaxed. Okay, stop that. The other thing that we have there is we have damping, which will allow the thing to come to rest quicker or slower. So no damping means it will go on forever and ever. That's not really what happens in the real world. But if we increase the damping, it comes to rest very quickly. So damping allows the object to come to rest quickly. We can also adjust the gravity. We're going to ignore that. I'm going to add in here the equilibrium position. So when the particle isn't moving, there's a line there that goes through the center of gravity of the mass, and we call that the equilibrium position, or the equilibrium line, or the center of oscillation. I'll probably just refer to equilibrium position in that case. Now, if I leave this go, if I pull it down, and I'm pulling it down half of the height of the mass, when I leave it go, the particle will oscillate or vibrate up and down, and the maximum height that it will reach will be the exact same as the amount I've pulled it down. So if I've pulled it down half of the height of the mass, it will rise to half of the height of the mass above the line. So there we go. And then if I increase the damping, you'll see that it comes to rest at the midpoint. Now if I pull it down a different distance, like so, it will go to the same distance above that equilibrium position. There we go. Increase the damping just to decrease that. Now I suppose we'll start here with what is a period for the motion. And a period is the amount of time taken for the object to repeat itself. So let's have a look at the periodic trace, which will show me the path that the object takes for one period or one oscillation. In other words, how far does it travel until the thing starts repeating itself? So when I leave it go, you'll see it here now in a moment. So that's our start point. It went to one extreme, down to the other, and it goes back to its start point. That's one period. So there we go again. It started at the midpoint, down, up, and back to its original starting point. And that's one period there, or one oscillation. So the time taken for it to complete one oscillation is the time, is called the period. And one oscillation is the distance it travels before it starts repeating itself. Okay, on to the next thing. Let's just put more damping there to slow that one down. Let's have a look at the velocity and the acceleration. The acceleration first, because the definition of simple harmonic motion is that the acceleration is proportional to the displacement, and they're in opposite directions. So let's pull this guy down. Now I've pulled the object down, so the displacement is downwards. The acceleration will be in the opposite direction, so it'll be upwards. If I push it up like that, the displacement is upwards, so the acceleration will be downwards. And the more I push it up, the bigger the displacement, the bigger the acceleration, basically. So let's do this. And we can see that, damping, get rid of the damping. And we can see that the acceleration is constantly changing. And the reason for that is, throughout all of its motion, the displacement here is increasing, increasing, and increasing, now decreasing and decreasing. It's increasing here. And because the displacement constantly increases as it goes up, the acceleration constantly increases as well. Now watch it going down. The displacement between that equilibrium position and the particle is decreasing. And if the acceleration is proportional to the displacement, the acceleration should decrease as well, which it does. Then remember, they're also in opposite directions. We'll also find something particular here. When the object passes through the equilibrium position, the displacement is zero, so the acceleration is zero as well. So there's no acceleration there, and the acceleration is a maximum when the particle is the furthest distance that it can be away from that equilibrium position. In other words, at what we call the amplitude. So the maximum displacement is the amplitude, and at the amplitude, the acceleration is a maximum. There we go. So acceleration a maximum at the amplitudes or at the extremes of the motion, and the acceleration is equal to zero at the center of oscillation, or what I refer to as the equilibrium position. Let's have a look at the velocity. So I'm going to have to show this slowly. We can see there at the center the velocity is quite large. And what ends up happening is at the extreme the particle stops, changes direction. So it stops, velocity is 0, changes direction. So the velocity is 0 at the extremes for a particle moving in simple harmonic motion, and it's a maximum as it goes through the equilibrium position. And these are things just to remember with simple harmonic motion.